NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. Thank you for joining us for the High Impact Thesis podcast. In this podcast, we invite researchers from NTU and across Singapore to talk about their research in a casual way. The goal is for them to share with people outside the research field that they are in a way that other people understand what is going on. At the same time, we know that there are a lot of other areas that are much broader than just the specific topic that you're dealing with right now. So, in this conversation, we're also going to spend some time talking about those broader issues. This is supposed to be a conversation, which means that you're welcome to share much more than the questions we ask. The questions are supposed to be merely guiding the conversation. And since you are the expert in this room, we want you to feel as comfortable as possible, sharing as much as possible. Thank you once again for joining us. To get started, if you met someone in just a few minutes to share with them what you do, what do you tell them?
Yeah, so I tell them that I work in managing and operating world's largest machine. The power grid is world's largest machine. Why it's called machine? Because it's a network working at same physical parameters. So technically that physical parameter is called frequency. But it's a machine. You can consider it as rotating a big generator, big roller at the same speed for everybody. And the energy it generates, you use. But I don't work on the side of generation. I work on the side how you get it after it is generated, how you use it after it is generated, how efficient you are. Now, biggest thing is, what do you mean by efficient here? That's what my research comes in.
Okay.
Consider, everybody has seen maps, right? You pick up any country's map. And you pick up a map which has roads, networks, highways, right? Very famous US map is there which charts all the highways in it, just roads, right? Now, what does road do? Road serves you? What highway serves you? Highway connects one point to another point.
Right.
You can drive a car from one point to another point. In technical terms, that highway is a graph or network. Now, replace this highway with wires. That's it. That the highway replaced with wire is power network. You don't know where the power is generated. So I always ask this question to the people, which basically explains what I do. So let's say you want to turn on your aircon.
Yes.
Right? You don't dial a phone to the power company and say, "Hey, I'm turning my aircon. Can I?" No, we don't do that, right? We just switch on the button. But when you turn on the aircon, suddenly you need more energy. You need just more power instantly. And instantly means speed of light because it's an electromagnetic wave. You just need it. Now consider a big shopping complex, right? The door is open in the morning, 8 o'clock, and somebody will turn on the aircon system, ventilation and aircon system, right? And it will be huge. Do they really call the person and tell even if it is huge? I highly doubt. No, they don't. So what a job of a operator is, they need to predict and prepare the grid to serve your demand without knowing 100% what you do.
Okay.
Or when you will turn on. So there is a big mathematical base and background behind operating this machine. I developed the methods to operate this machine safely, efficiently, and later on we can go in details of what I mean by efficient. But basically, in a single line, I work on methods which safely operate this machine and efficiently.
So if I may ask, your work therefore is on the transmission side, on the distribution side, or
Okay,
or
so
you don't really think in those kinds of
yeah, I don't
categories.
really, I am kind of a outlier in that sense. I don't think in a that way. So let
Mm-hmm.
me frame it in a different context. So in any network of any kind, whether it's a gas network, power network, or traffic network, which is highways, right? There
Mm-hmm.
is a fundamental problem called flow. In my
Okay.
problem, it will be called power flow.
Mm-hmm.
In some other network, it will be called gas flow. So what is flow? So let's say you drive on a highway from point 1A to B,
Mm-hmm.
right? So your state means where you were was point A, then you will have some parameters, let's say speed and direction, and then you will reach it after some time t to point B.
Mm-hmm.
Control was where you want to drive, and your state was, in simpler term, your location.
Mm-hmm.
I extrapolate that to power system and I say that you demand power, but that power is served to you based on some states called voltage.
Mm-hmm.
There will be somebody generating power, so there will be a generation decision.
Mm-hmm.
All this combined together, put in a mathematical form, you need to know at what state power system is right now working on.
Mm-hmm.
Plus, if you change something, what will happen?
Mm-hmm.
So
Okay.
that fundamental problem is called power flow.
Uh-huh. Uh-huh.
Now, that problem exists in any kind of grid:
Mm-hmm.
transmission grid, distribution grid, microgrid, smart grid, you name it, right? There will be a
Mm-hmm.
flow.
Mm-hmm.
I work on that fundamental problem of power flow.
I see. I see.
Then
So,
special cases based on approximations are developed for the distribution or transmission or whatever is my target for that particular
Mhm.
work.
oh, right. I think that's a that tells us the basics of what you do. I think I've got the other question is really what is the motivation to work. I think I've picked up what this is about. You know, you're trying to make sure that I, as an individual, don't have to worry about these other things.
Yeah,
When I want power, I
yeah,
want it to be there, and so you work on the
precisely.
math behind enabling that. Right?
From your point of view, yeah, you should not be worrying about this.
Mm-hmm.
From the guy who is serving you power, he want to give you cheap. From the country you are in, want cheap power for progress, but also in current context want to mitigate carbon emissions.
Mm-hmm.
So it depends from whose point of view you are looking. From
Mm-hmm.
your point of view, you want to use cheapest power.
Mm-hmm.
From my point of view, from grid point of view, I want to maximize my profit maybe.
Mm-hmm.
But if you are a government entity, you want to make a balance
Mm-hmm.
that your people get a affordable power, but
Mm-hmm.
your company gets some money so that it can progress, innovate,
So
right?
different
So
stakeholders want
yeah,
optimize for different things.
yeah, and then that angle becomes very crucial when you attack it.
Mm-hmm.
Whether as an are you looking from operator side, consumer side, or I we call it independent service operator, basically a body over it which makes rules, just rules, don't own anything.
Mm-hmm.
Like government, you can presume it a government, so you need to be very carefully picking that angle of attack.
Mm-hmm. Okay. So I think we'll move on to more very much in detail to what you do. I think I'll let Ahmed take over.
All right. So we've yeah, like Christopher said, we had an idea now about like the overall overarching like topic that you're trying to tackle, right? So let's get a little bit more into the specifics. Um, so you're talking about power flow and managing the efficiency and like making sure you get the power that you need when you need it. So when you let's say um, at the beginning of this work, when you basically started doing this research, what sort of questions did you have like to you know to address, and then how did you reach like from that point at the beginning to where you are right now? I assume you just finished 3 years of PhD, is that right?
Yeah, we'll be finishing in July.
Mm-hmm.
3 years. Yeah. So mm, my journey of research is a continuation of my master's in sense.
Mm-hmm.
So in my master's, I developed a sense that, so you see, electrical engineering is somewhat, if I there are two fundamental things in electrical engineering. engineering, right? If I bifurcate it into physics, math, and chemistry, I can say it's 70% mathematics, 28, 29%, or even 30% completely physics. There is no chemistry, right? It's math and physics combined, right? Once you formulate a problem and you understand that how power happen generates and it's an electromagnetic wave and electrons, as an electrical engineer, I no longer concerned about the physics part. Mostly I express the laws of physics like Kirchhoff's laws and all in mathematical terms, and then the only challenge remaining is how you solve it. That's it. How you formulate, how you achieve objectives. So in my master's at the beginning, I got this idea by going over literature that basically power system is nothing but a mathematical problem set. It's a work for applied mathematics, control people to attack problems from math side, seeing viewpoint, and then relating it to physical world. It's a big link. A pure mathematician cannot jump in because he will not be able to link it how it is linked to real physical world. So it's not like us. So all the examples I gave till now are all physical networks. I did not give an example of a social network. That is also a network, how you make friends, right? But that's different. That is not governed by the laws of physics. There is no laws of physics. The moment you unfriend somebody, that's gone. But the line, there is a power on the line. So the disconnection of line has ramification across your whole network that may not exist in social network, right? So that's why. So then I started exploring the mathematical side of it slowly, because my background is not math, it's an electrical engineer. Then when I joined here, I had a kind of idea that what kind of work I want to do, and that was more exploration from the side of mathematics to the power. It had a few objectives from my point of view. One was the questions I'm going to ask should lead to more tools learning for myself. I don't want it to end my PhD with knowing as much as I knew and just publishing papers. And the second was that, so there are a lot of angle of attacks to the problems we do. So one attack is how can you develop more and more applications, which is predominantly how power researchers ask questions. What can I do with it? I wanted to ask questions where everybody lead to. That's why I focused on fundamental problem of power flow. So the question I asked is that, as simple as that, okay, we solve power flow all the time for every problem. Everybody solves power flow who is working on power system. What happens when some uncertainty comes in? Do we have efficient methods to solve it? Simply, what is the state of art method to solve it? Can we interpret them? So I started asking those very fundamental questions. My journey started from a problem in PhD called small signal stability. It's about a system. If you push it a bit, will it come back to its original state, or it will just go away?
And what do you mean by push the system?
Push means, let's say you have a pendulum, right? And you just touch it small. That small is not quantifiable in mathematics, but it's just a small delta, right? It should not be a sudden big. Small, you push it means you change its input, or you change how much power you want. Something happened. Let's say you were working and something happened. Let's say you switched on the aircon suddenly, big aircon. So it's a small push when you see in the context of grid. So now what should happen? Ideally, what should happen is grid should go to that point, serve your need, and then come and then start properly working. But that depends on how much grid was stable at the initial point before the push. It becomes a very difficult mathematical problem, and you define stability based on eigenvalues.
So it's
Matrix.
So the way I'm understanding it right now, it's not only about how much power is available in total, but there are other factors as well.
Yeah.
Stability.
So one important thing about power network, which generally people who are not from power network side don't understand, is it's an instantaneous matching of load versus generation. It travels with the speed of light at current movement. the amount of power generated in the world almost equal to the amount of power consumed in the world. You can't have a situation where there is a deficit. Some parameters will go beyond the control the moment you generate a deficit, right? So in that context, it a lot depends. Think like this. Let's say you have a slippery, hilly region where you are walking, right? You will end up in at some point which might be at such a slope that if I push you a little bit, you will fall. But there will be some point in that same hilly area where if you are solid enough, if I push you, you might go back a bit and then can come back. But you can't do that at a steep slope. If I push you, you will just go. In that slippery region, I would like to operate my system at a point where if I push the system a bit, you mean system, then you can come back where you were. So there are challenges. So see this question in this context. If you know where you are standing, checking whether that point is stable or not is a cakewalk. Literally a cakewalk, because you are standing means a coordinate, right? Coordinate means a matrix, and checking matrix eigenvalue is a straightforward problem. Everybody knows it's like undergrad first year problem. Then can you find that point is a whole together different story. So the angle of problem attack one is checking the stability of a point. The second problem, which is more difficult problem, is finding a point which is stable. And this is just a plain simple problem. Then you add over it other constraints such as whether that point might be stable but may not be feasible for other reasons, may not be economical. You don't want a stable point, but it's too costly. Nobody would like to operate there. So then it increases layers of complexity.
So this point you're talking about, you're talking about is a point in state space, or what when you say point
state space, precisely state space. So I'm talking about a point in state space. So if you give me a point in state space, I just need its system matrix, and I just take eigenvalue of the matrix. If real part is less than 0, the system is stable. Period. But can you find that? Then it becomes a different story, because calculation of eigenvalue is based on solving a matrix inverse. And then the problem is that searching on a multi-dimension space, such a point where all eigenvalues are negative, is a problem which belongs to a class called NP-hard. So NP-hard basically is a problem where we don't know if there exists an efficient algorithm to solve that problem in simple terms. So the question, Ahmed, the question you asked is like, what kind of question I asked? So the question I asked is that, I don't want to prove a point's stability because there are methods. Can I find that point? First question I asked is this. And by going through some work, it was clear to me and my advisor both that we cannot do it by the conventional methods. Conventional means the state of art way of looking at it from eigenvalue point of view. So what we did is that we started looking it from the different angle, which is called Lyapunov type stability, and we constructed something called bilinear matrix inequality. So it's nothing but a quadratic equation, like x square plus x plus 1. Just that x here is not a number, not a vector, it's a matrix. So we developed a condition over such an equation that if this equation is true, then system is stable. So that was my first work. And then I superimposed that equation under economic and operational constraint and formulated a big problem, which is called small signal stability constrained optimal power flow. Basically the same power flow. Optimal means you put an objective. Easiest and most common one is economics objective, want cheap power, and then you constrain it based on stability. You say that, okay, I'm interested in a point where I can serve the cheap power, limiting all the constraints of physical and network, but that point has to be small signal stable. So the question becomes is, can you find it first? Biggest question. Let's say you have a magic and you found it. How much more money you need to spend in comparison if you look for an any point or stable point? So that balance was my first paper, or you can say first initial work, and it took a hell of, I think it's most difficult work I have done till now by far. That was my first PhD problem. It took 2 years to 1.5 years to publish in a journal, 40-50 pages of reviews, and then this is some work, like some amount of, you can say, and it's more important in that context, in same question which angle of attack you choose.
Right.
It can
Can
become
you tell
really,
us a little bit more about the like some of the challenges that faced you during that period
yeah.
in
So
that
first challenge,
work?
first biggest challenge was that I don't have a math background, and this problem is not a power problem, as I told you. This is a purely mathematics problem. There is nothing power. Everybody knows this, right? That matrix construction is cakewalk. Everybody knows it. It's really undergrad electrical power system basic course stuff. So the biggest challenge was to see from its mathematical point of view. So I don't have a math background. That was a big challenge. So what I did is that I have a theory which is maybe wrong in many contexts, but it works for me. So it works for me. So what I do is I just concentrate on the thing which I need. I mean, you give me a book, I won't read it by cover to cover. Whether it's a math book, I will try and find the minimum 5-10 pages which are needed, and pages needed to understand those 5-10 pages. That's it. That helps. It may be a wrong approach from a purist point of view, but it helps me because I believe I am not here to recite what people have done. My job is not to write a book on a topic. My job is to construct new knowledge. And unfortunately or fortunately, the amount of knowledge already created is so huge, you can just assimilate it in 1 or 2 lifetimes. You cannot produce anything new. That's what I think.
Right. And
Right.
what you're
So
doing is more or less following the 80-20 principle. So basically do
yeah,
20% of the work to get 80% of the rewards, right?
I don't see as a reward, but my point is, like, let's say, so for an real example, I wanted to needed a norm, right? Norm means Euclidean norm or this norm and that norm, right? So we found a norm which can be negative. It's very counterintuitive, but it's a logarithmic norm. It is called, you can prove all the properties of norm, and this norm can be negative, right? So there was a book, big book on norms or control system, right? It had 3 pages only on that norm. That's it. It's an old book, not used very famously. That norm is because it does not fall in your Euclidean space and all, but it is used to bound the matrix eigenvalue. Basically, it can say that all the eigenvalues will fall on the left hand side of this norm. So in a way, if I can show that norm is less than 0, all eigenvalues will always be less than 0 for that particular matrix. Then that norm may be much easier to calculate. So it's a simple logic after you found. Problem with, like, I face with my kind of work is I don't know what I'm looking for. So because I don't know what I'm looking for, finding what I'm looking for is more difficult than actually finding it later. So that is the biggest challenge. So I phrase it like this: you can't search math on Google. That's the biggest challenge. You just can't. You just don't know whether that exists.
Right,
So,
right.
so what I will do is I will read those 2 pages, learn that norm, use that norm, and go forward. I don't know what comes at page number 23 if I stop at 22 on in that book.
That's an
Yeah. So
interesting thought.
this is one challenge, and second was bigger than this maybe after doing it, is to explain the idea that much mathematical idea to a community which may not be that much mathematically involved in it. Constructing mathematical logics, my advisor helped me a lot in that. He literally taught me how you construct from one line to another line, teaching me even meanings of symbols of each, even going to that so-called low level, that teaching me every meaning of every symbol. But then telling it to the people who may not be that much mathematically ready, but they are practitioners of power engineering. They are interested in problem more than how you solve it, because they don't want to go into that mathematical depth. That's not their job.
They just want the
So
solution.
explaining them, the logic behind it,
Hmm.
the one more thing is that I personally put a lot of focus on motivation of using even a method, not only motivation of doing a problem, but why you certainly needed that step, how
Hmm.
on earth you stumbled upon from A to B that you need logarithmic norm. So that's what I explained you, for example, that I needed that norm so that I can calculate something easily, but I bound all the eigenvalues that they will be in left hand side if I prove just this norm to be left hand side or less than zero. So these two big challenges were there in that first
Okay.
work.
I got two questions here. So the first one, like when you talk about the eigenvalues and the state space matrices and all, can you tell us more like about how you come to construct these, formulations, mathematical formulations from the physical, or like what does the data come from? And then my other question would be, is this the only way to tackle? Is this the only like method to tackle such problems, or were there like other methods that you considered and then you decided to go with this um, this purely mathematical one? Yeah.
Yeah. So first one is how we construct it, right? So any system which has motion, or in technical terms called dynamic, has a dynamic model. So dynamic model of power system is there, which relates your angular speed with your mechanical and electrical power in turbine. Think it like as a you can say a car which is moving. So there is an angular speed, there is a force you are applying, and then there is a speed, vertical speed, and then you can balance it out basically with time, right? So angle difference, angular velocity, and all these things, these mathematical model, there is a mathematical model in we the mathematical model for power system is called differential algebraic equation set. What it means is there is a component which are differential equations, d omega by dt, how angular velocity evolved with time in relationship with power generated and mechanical power input. And there is an algebraic equation set which relates to basically nothing but Ohm's law through Kirchhoff's currents and voltage laws. Ohm's law means power balance. Power balance means the amount of power comes in equal to amount of power goes out from a node. I'm ignoring the losses, but you can add just the losses. So but you need to have a basically conservation of power in the same way you conserve the node, because let's it's like this. You are uh, you are sending water from one inlet into a pipe. Imagine like this. Let's assume there's no water sticks into the pipe. There is no way that if there is no leakage that it won't come out at the same. So you need to have balance at both ends. So when you combine that, that becomes a differential algebraic set. Now, for small signal stability, you linearize that set, right? Here comes the biggest contribution of our work. When you linearize at a point always. Any linearization is at a point, right? In general, at a point means you put a numerical value. The moment you put a numerical value, your relationship is only valid around that point,
Yeah, exactly.
right? But then you can't search a point, as I said. Then you can just prove whether that particular point or any point nearby it is stable. So
Mm.
what we did is we formulate the differential algebraic equation as a quadratic set. Means as a quadratic equation, we manipulated the variable. For example, what we did is we call sine theta as u, some u, and then make it a and manipulate it with the problem such that it becomes in terms of u square, v square, all terms in quadratic. Once you differentiate quadratic equation, it becomes a variable form. So there will be a u left, 2u. So now my model is you can put a u and check whether it's in a variable form rather than in a numerical form. So
Mm-hmm.
when you get in a variable form, now I can play with it. I can play with it means I can say what is the maximum value of u such that this equation is less than zero, for example. Now I am not fixed at one u. So look from that point of view, I needed an entirely new theory of Lyapunov type stability and bilinear matrix inequality. So that is how we link the physical system to the mathematical side. And second part of your question is that is there any other approach? So the classical approach is eigenvalue based, right? Another approach is Lyapunov type approach. But you see, what I experienced over the time on working on this problem particularly is there is a point where all these are linked. I can always link the eigenvalue approach and Lyapunov type approach. They lead to the same criteria. What they are different point of view mathematically to look the same problem, which is physically the problem is same, but mathematically you can attack problem differently. Now the question which used to come in my mind very often initially is why you need two approaches, but its answer lies in the whatever I did is that there are issues in one approach where you know what you need, but numerically you just can't compute it. For example, computing eigenvalue is very difficult than computing logarithmic norm. It's a straightforward thing. And if my condition is that I just need eigenvalues to one side, I then and my logarithmic norm bounds it, then logically I just need logarithmic norm to be that one side. So mathematically, what people try, so this nothing in this foundation work of relating stability with math is my work. My work is to interpret it in a such a way and formulate my problem in such a way that I can use mathematical tools developed over the years to solve that problem. So the line of attack maybe there may exist a third line of attack other than Lyapunov type or this type. There is one. So which many people will be more familiar with electronic side is frequency based approach, Nyquist plot and all those stability approach, right? So there is that attack, may be worth exploring also. But then comes the challenge that how far you want to go from a standard practice, because ultimately I work on a system which need to be implemented. It's a physical network. The more far I go, the lesser chances it will be ever adopted, because then both system wise, understanding wise, the changes needed will be huge. So they may just overcompensate the benefits I'm providing. So it may be a good exploration for intellectual purposes, but it may fail, may or may not be as good at in that sense.
I mean, that's a very critical point, I would say, during a PhD, like when you have to decide on different approaches, right? Like, do you want to get the skills that will make you, I guess, more useful in the
a better researcher in general terms.
Right, better researcher and like more relevant to nowadays. Maybe you'd like to be hired in a research institution or a R&D department in a company, and you would like to, like you said, be closer to the standard approach and be familiar with what others are doing. But also the flip side of that is also doing something extraordinary. I mean, it doesn't have to be extraordinary, but it's just so different from the status quo.
So if I get your point, so I measure it something like this, that how far I am from the whatever is the norm. So my criteria is not how far I am from in terms of method from the norm. I will consider any method if it does the job for me. So over the years, I have developed this understanding about my work is that I'm not developing new methods, right? I would like to have a nameplate over my office, whatever office, wherever I will have, is as a problem solver. I'm a problem solver. I solve problems. So as an individual researcher, I don't care literally what method is used to solve that problem, whether it's new, old, till the time it just solves the problem. So it's a very clear distinction in my mind that what I am looking for. I am looking for solving a problem. Method is just a method to do that. Literally method, I take method as a literal sense. I don't take pride in using a particular method, say very famous method, deep learning. I don't take pride in being a deep learning researcher, because in my opinion, I'm not, until unless I'm developing new deep learning methods itself. My job is not to develop a new method. As far as till now, my job is to solve a problem by existing method, tweaking a method, Even if I develop a new method, I will develop that in context of that problem. I never attack that as a generalized method to solve a general class of problem.
Right. So if I get you correctly, then it will be like if let's say a new tool is available. Let's say machine learning is this new tool, but you're not quite sure if it will uh, achieve your targeted results, right? So you wouldn't actually consider it com- compare with something that's already established and you know that it will actually work for you.
Yeah, precisely.
Mm-hmm.
I want to ask a bit on this same topic, really about you. said you were at some point you are more an electrical engineering person than a mathematics person. I'm just wondering for the general PhD student listening to us today, how did you how did you go about incorporating math or trying to find out what would be relevant for your work? Is it just going to the library and reading? Is it more asking people? Is it how are you
Mm,
constraining yourself since, like you said, there's a lot of knowledge out there?
yeah, so it's a process, I believe. Like, so one thing is that it does not happen overnight. The clarity comes very slow in a subtle way, and most of the time we don't even realize whether we are making any progress or not,
Hmm.
right? So just a quick background kind of thing is that I have been wanted to do PhD since I was in my bachelor's third year, right? I
Hmm.
published, not in the sense of published something big, but first introduction of me to publishing in a conference paper was when I was doing my undergrad third year. So
Hmm.
it's a long term project for me individually doing PhD. Just did not landed up doing it, wanted to do it, train myself to do it.
Hmm.
So how you find is one is that very big thing is it's like, so it's like in a normal our age reference, I can say that the topic what you want to do or the problems you want to do or even the angle you want to attack is like a relationship. No matter how good your partner looks, how good a person is, if you don't like it, the relationship won't work. Simple. No matter how good it is, you need to like it.
Hmm.
So if I have a natural inclination to look, I like reading math. I don't understand it. It's very hard to understand. I'm poor at it. I know. Still, I like it. That makes everything sustainable.
Hmm.
So I go for things which I like. They may not be good, may not be fashionable, may not be trendy. I
Hmm.
just like it somehow. Sometimes I don't even have an explanation when I begin. It's like, let's say you read three papers today, right?
Hmm.
You don't know about their relevance and importance. Certainly, as a PhD student, particularly when you start, you even don't know whether which topic will be hot to publish. You don't know,
Hmm.
right? You don't know many things. So, how you decide which one to choose? I always choose the one I liked. I don't
Hmm.
care how many citations that paper has. I don't care whether it's an old method. For example, power flow. Any power system guy will tell you it's a rubbish problem. No longer publishes paper, which is true up to a certain extent. Optimal power flow and power flow are most fundamental problem, and people no longer work there because it's bloody hard to publish, to find new work. Everybody solve and works on application, 90% people, which solves them by any existing tool and do some micro grid, smart grid, some demand response, some kind of problem.
Hmm.
Or a different class is that everybody works on machine applying machine learning methods to to the old problems. So
Hmm.
it works like this. You have a method developed by somebody, you have a problem proposed by somebody, you just apply and move forward.
Hmm.
I don't like it for some
Hmm.
reason or another. So I don't do it. So my
Hmm.
inclination is very simple. I like it, I go for it. Does
Hmm.
not, and I almost don't care about how it is seen by people. The biggest example is my other set of work in my PhD. Everybody in machine learning right now works on at least neural network, if not deep learning, right?
Hmm.
I work on a method which is based on a theory 100 years old. I work on statistical learning, Gaussian process
Hmm.
for a particular reason. I like it.
Hmm.
I like it. It is explainable. I
Hmm.
like it. It's not a black box. And it suits my purpose of giving me a form.
Hmm.
So, in quickly, I can explain that if you apply a neural network, it's a black box. Biggest
Hmm.
problem or challenge with neural network, which people are trying to solve, is any kind of neural network is it's a black box. You don't know what's happening. and you don't get output as a mathematical equation, right?
Hmm.
I work on a method called Gaussian process, which gives me that equation
Yeah, I saw your
after
work here
approximation.
on Gaussian process learning based probabilistic optimal power flow.
So yeah,
That's
so yeah, that's one of my publications. You just, I
okay.
think, opened up. So it's like this, that why I picked up is that method has a motivation, and that
Hmm.
motivation clearly is, does it suit my purpose to solve that problem?
Hmm.
Mo- Left and right, nothing matters to me. It's not a hot topic. Nobody use. I think we were the first one to introduce it to solve power flow and optimal power flow. It's a method which people use for forecasting because it's good. That's it.
Hmm.
Time series forecasting. Many people use for general time series forecasting problem. We were the first one to introduce it almost to use for analytical and operational problems, behavioral understanding. Power
Hmm.
flow is nothing but understanding the behavior of that net system. So why we did it? Because it serves the purpose the way we wanted to look at the problem. And
Hmm.
more so, like, more time I'm spending in research, the more I'm coming to a situation where, in example, I take 2 months to think about a problem and formulate the problem, 15 days to solve it.
Hmm. Okay.
I don't care method is fancy or not till the time it serves the purpose. That's why I can solve it by any method. It's okay. I look for new method when I have a problem which is not solvable by the method I'm attacking or the by angle I'm attacking it
That's
from.
interesting. So you spend a lot of time finding a problem that really needs to be solved, and then
Yes, really
you
need to
use
be
whatever.
solved is a kind of ambiguous thing. Really need to be
Okay.
solved by whom? Till now, it should be really need to be solved by myself. I should
Okay.
be interested in that problem. Till now, I'm not reached to the honestly to the level where I go and think whether it's practically possible or not. It's
Uh-huh.
more. It can be a just pure exploration problem. Even fully knowing that it may not be ever land up in a practice, still I can go for it if I just like it.
Okay.
If I like to work on it, bang, I will go for it. If I
Okay.
don't like to work on it, it's very difficult for me to you know motivate myself to hit it.
Mm-hmm. So you're leaning now more toward being you mentioned a moment ago that you're more a problem solver. So you're
Yeah.
less a mathematician, less an electrical engineering person, and more a problem solver. And these are
Yeah.
the tools you
and
use to solve problems.
and there is a very important point which anybody who works in my area will understand, that mathematically my area lies in so many domains that you cannot be expert at all. It borrows from linear algebra. I work purely on uncertainty, so it borrows from probability theory. It borrows from all the optimal control theory based work, all the machine learning. You just can't get graphical graph theory. You just name it, differential equations. You can't
Mm-hmm.
just be an expert in any of the areas. All, even none of the best pure mathematicians work on more than one or two areas. So
Mm-hmm.
that's not my job also. Slowly I built that understanding about my work, is that math is a tool
Mm-hmm.
which I'm not developing. It's very important to not have a notion that I'm developing a method. I'm not. Most maximum what I'm doing is I'm twisting a method or intervening within a method in between, that an output which may not be suitable for others, the intermediate state output may be useful for me. So I understand a method to use it for a
Mm-hmm.
problem solving.
Mm-hmm. Okay. Okay. So that really is very specific to your work, and the next section is really more speculation related to your field, but also somewhat distance. So we expect that some of it is a bit of guesswork, and some of it might not be exactly a research area. But we want to hear your thoughts. I'm interested in understanding at the beginning of time when electrical grids were being created. There wasn't this level of sophistication that we're talking about right now, because obviously they didn't have computers. They didn't have, I think they probably didn't have the math, the way to model things the way that we do right now.
Hmm.
So I'd like to understand, what does
The
like
origins of it.
yeah, where did it come in, and how much difference does it make, or in general, why do we have it? Like, I understand there is a need
Yeah.
for it, but
So,
maybe it seems very
uh,
complex, and a lot of work schools spend time training people to do it.
so it's like this, that So the it's a very fascinating story about electrical grid because it comes from war of two geniuses, Edison and Tesla.
Mhm.
Thomas Alva Edison and Nikola Tesla. Their war generated the grid we see,
Mhm.
literally the grid we see. So what they did is there was something called direct current based electricity generation. So
Mhm.
there was a company called Edison Electric, of course, by Mr. Edison himself. So what they used to do is they used to put a local generator, let's say in Manhattan, and few blocks of it will get power from that,
Mhm.
right? And then other blocks, one more. But then there are challenges. One is it's not efficient.
Mhm.
It's very poor generation in the sense that you have a very localized, not something called economy of scale is not there basically.
Mhm.
And then you imagine having a generator in NTU, powering NTU, the kind of gases it will have. You need to bring coal to this place, right?
Mhm.
To power it up. So then people started thinking about, okay, let's say, can I generate it far and bring it back? So
Mhm.
that's where network comes from. You generate it far and then bring it, but you they could not do it with the DC current because it's direct. It has a lot of technical difficulties, losses, high scale generation has problems, a lot of things. Here comes the genius of Nikola Tesla. That guy said, okay, let's do with the alternating current. He built the entire model, bids it in, shows it in a show, basically in a network, and long story cut short, he wins the tender for a Westinghouse company to generate power at the Niagara Falls.
Mhm.
Just Google it, see how far Niagara Falls from New York or any load center in America is. The only option they had is to lay down a grid.
Mhm.
So first they lay down a grid, which is bulk power transmission system, which we call in short, which transfers high amount of power. Then they said, okay, we have high amount of power, but I cannot feed in that high amount of power to every house. One, they don't need it, it's very costly. Second, it's very risky to feed that much power together. So what they did is they lowered it down in terms of power level and voltage level, and then they constructed something called distribution grid,
Mhm.
and then which comes to our house. Then the levels of it and intricacy is constructed. But so it's important to understand that it's not a new phenomenon. We developed it over 100 years.
Mhm.
So the grid is not developed overnight, or in, let's say, like, it's not like a mobile phone, right? So
Mhm.
that's a big difference. It has a lot of physical infrastructure,
Mhm.
and anything you propose means ramifications economically, socially, a lot.
Mhm.
You just can't propose anything like wide, so because it need to change a lot. So for example, the newer countries in the sense who had a recently developed grid, like let's say China, India,
Mhm.
Singapore,
Mhm.
they have a much modern grid than the developed countries like USA. The US
Right.
grid is 60 years old
Right. Because they
because you
didn't
just
have the
can't update it overnight. Yeah.
right. Because now there's
So this
this
is
map
how.
that we have, so that when you build a grid today, you have access to the tools that you guys are developing.
Yes,
So it
yes,
should
yes.
hopefully be much more efficient and
Yeah, and there
reliable.
is an entire research area called planning problem, which just
Mhm.
plans grid. Nothing. They don't
Mhm.
operate. They just plan how efficiently you can plan the
Mhm.
grid.
So
So
and
this is
then
the origin of the grid.
mhm. So I have read a little bit in this field, and I hear that uh, high voltage or DC is becoming a thing again. Could you
Yes.
say a few words about that? What's going on?
Yeah. So
And
DC is becoming a thing because there is a new research, something called power electronics. Thing like this. Generating DC is difficult, costly from conventional sources.
okay.
Renewable sources like solar generate DC nicely.
Mhm.
One contradiction. Second, if you have up to a certain length of transmission line, transferring DC is costly. Why? Because you need to lift the voltage at that level. There was no mechanism to lift the voltage of DC before. Now
Mhm.
you have it in terms of power electronics. So now you can play with DC all as same as you can play with AC, whether it's voltage level, power level, or anything. So now all the other benefits DC had are coming into the picture back. So that is why DC is coming back. And now big talk is, can we use the existing network for DC, more
Mhm.
so on distribution level?
I see. So is it more going to be a future? Is it going to be a future of more AC and DC, or is it going to be a
Mixed.
transition toward
Yeah,
DC?
mixed is the future.
Mm-hmm.
Mixed networks, mixed generation, mixed transmission, mixed distribution, and mixed appliances
Mm-hmm.
is the future.
Nice.
It's already mixed, right? All your electronic devices works on DC. You just have a charger which converts it into AC into DC. So we don't realize it, but it's already mixed. Your more and more our uses, the
Mm-hmm.
way we use power is more and more into DC now.
Mm-hmm. And I think another thing that obviously people outside the electricity field don't understand is why we don't yet have wireless electricity.
Ah,
Where we
yeah. So
are there any advancements in technology or
yeah, there are
research
there are
that
there are
would
advancements.
like
There
to?
are advancements. Problem is not so as a proof of concept, power DC or like wireless power transmission is proved way back. The
Mm-hmm.
problem is the quantity,
Mm-hmm.
the amount, right? You can charge your phone, but can you get enough power that you can feed entire NTU? That's when the problem is. And then when you do wireless transfer for long distances, that energy, basically you are sending energy in any form, right? The amount of energy interact with the atmosphere. So you can safely say a large amount of power transfer for a large distance is a very far, because you need that amount. Not It's not about receiving and sending. It's about
Mm-hmm.
what happens when it interacts with the atmosphere. Large amount of energy sending means large charging of air around it. Even
Mm-hmm.
now when you have wire and large amount of energy at high voltage transfer, there is something called effect, like, and nowadays it's a bad term, but it's corona effect. So you have that effect, and
Mm-hmm.
then the air gets ionized. There is a physical problem, there is an atmospheric problem, there is a buzz sound like zzz, continuously. That's why you cannot have high transmission lines near the residential areas.
Mm-hmm.
It's challenging. So
Mm-hmm.
even with the wire,
I
now
see.
imagine everything is in air.
Right.
So
And
it's wireless transmission is more. So two concepts: wireless transmission and 100% renewable. These things are for the non-electrical engineers. Only those
okay.
people think that this is a close reality. I'm not
Mm.
saying it will never happen. As a scientist, I cannot say it will never happen,
Uh-huh.
but it will definitely not happen as fast as non-electrical engineers think.
Cool. And I'm interested in wireless power because there's always been, as a space engineer, there's always been reports of someone trying to do power from space. So you put out the solar panels in space, then you turn it into microwaves, and then you transmit the microwaves to the ground, and you receive the power on the ground. That way, you have
Yeah,
still
but
have 24/7 power.
you can
Uh,
do it by concept. Nobody is stopping. But the microwave which you are sending, the amount of power, it's not about loss also. The
mm,
amount of power you can do it by that way is the big issue.
mm,
How much you can do it? Of course, we have, let's say we have a mobile network, so we send waves, right? We have a satellite network, we send wave, we receive wave, they have energy.
mm,
But whole process of that is how you can do better communication with low energy. Why low energy? Because you don't want to transmit more energy. It leads to cost and problems,
mm,
simply.
Mhm.
So that is what the so a layman's question can be: what will happen to them if anything comes in between those microwaves? Will that thing will get cooked?
mm. Hopefully not. But yeah.
Yeah, I know, but this is how it evolves when you go to the higher energy levels, basically.
All right, Prakshit, I think that's really it specifically about your research and about electricity in general. Very interesting topic. I mean, it's probably one of the greatest inventions, like you said, this big machine, the power grid, but also electricity itself. It's like it really is an empowering technology, right? The things that
Yeah,
we're able to do right now,
I,
it's really
I think it
incredible.
will it will come in a list in top three, top five with fire and mobile, maybe with
Right?
human interventions. Yeah,
And it's like, like 1800s, I mean 1700s, let's say perhaps you couldn't speak something like sell electricity. It wouldn't make sense, right? It's like
yeah, yeah.
they didn't even think
The
about it.
word
But now
the
it's
word
like
did not exist. I believe the word did not exist back
That's
then.
yeah, that's true.
I mean, yeah, they thought about it in a very different sense. So today we talk about it and it's concrete and it's very
Yeah.
interesting. So very, very nice field. I think for now we'll move on to your life.
Right. your your yeah, your personal life, but not your private life, of course. But basically, what do you like to do in your free time, and what kind of activities
So
you're interested in?
yeah, so I developed a very like a vast range of interests. Like you can say in single sentence, you can say that I'm a nerd. So I look everything from the nerd's point of view, a studious guy's point of view, but I have varied interest. So let's say, so I keep on trying new skills. So when I came, I started learning swimming. I'm from a place in India which is kind of a desert, right? So we don't have that much facilities or rivers naturally to have swimming facilities and all. So I learned swimming. Then I went for scuba diving. So developed an interest in travel a bit. Traveled the two, three things. COVID spoiled.
You're going like going deeper
Yeah,
and deeper into the water.
deeper and deeper into water. The COVID-19 just spoiled the party, but I am hoping once it eases out, I will start again. Then I bought a camera and started doing
Hmm.
basically city landscape photography, no portraits. I don't like shooting portraits of mine on people, but I bought a wide angle lens so that I can shoot. So we went to a city in Malaysia called Penang, right?
Hmm.
So it's basically a city which has street art, lot of street art. So because it has lot of street art, I had lot of street photography.
Mm.
So
That's nice.
for a long time, I'm thinking to write a blog on it about Penang, the art gallery. So it's like a gallery, whole city is like a gallery for the things, right?
Hmm.
And I write blogs. I wrote about all my friends' journey to their PhD, how they ended up doing PhD.
Mm.
I
Wow.
post them on my blog. Recently, I bought a ukulele and trying to learn that now. Other than that, I write poetry mostly in my mother tongue, and if you know a language called Urdu,
Hmm.
it's near to my mother tongue, so I write poetry in that. Read books, and there was a time when
What
I
type of
was
books?
uh, mostly biographies.
Hmm.
I'm a movie buff, literally a buff. Netflix mostly don't have anything new for me to offer, which is good. I'm at that level. Watch certain movies, I watch like 50 times, 30 times. There is a set of movies which, if I'm feeling low, there is a set of movies I will go and watch. So one
Mm.
of them is, for example, Cinderella Man. So it's not about Cinderella in Cinderella, it's about a boxer, real boxer in 1930s. It's a movie
Hmm.
about boxer. So it's one of my favorites. One
Mm.
is because related to my work, and one is biography of Ramanujan. So basically, it started. So I forgot to tell. Maybe it did not occur to my mind that my journey to explore more math started because I read his biography, the book. The
Mm.
Man Who Knew Infinity is a book,
Hmm.
right? And the very interesting thing about that book, people should try. It's written by a professor at MIT who is a professor of scientific writing, and he
Mm.
writes in the books, I think preface or somewhere, that if I ignore mathematics of Ramanujan and write about Ramanujan, then it's like writing about a painter without paintings. So
Hmm.
that professor distills that very typical difficult mathematics to a term which I almost can, not 100%, but can reach and understand. It shaped up my understanding and desire basically to look. Of course, there is no comparison between what we do and what Srinivasa Ramanujan was. Like there is no like, it's like, need few lives to reach maybe there, but it at least sparked an interest
Mm.
to look things in from more mathematical point of view. So I would highly recommend anybody who listens to this talk to read that book. Not only movie, read that book.
The Man
It's
Who Knew Infinity, you said.
The Man Who Knew Infinity, and it's particularly interesting because it's not written by somebody who don't understand the math. It's written by a professor at MIT, and it particularly makes the book more interesting because he writes about that math.
Mm-hmm.
So
Right.
that made me interested in one more thing, which is now more of a hobby of mine, is that I like to understand how people think about their research.
Mm.
That's it, nothing. I don't. So my friends, their research areas are so varied, but I always interested in how they think about it, fundamentally thought process behind origins,
Mm.
how they think. I go to talks, I ask questions about thinking. I'm not interested in the problem they are doing, even if they are in my area. They are doing their problem, I will do mine. That's not a problem. But the question is how they think. And it's
Mm.
not easy because it's very difficult to articulate how you think.
Mm-hmm.
Even I cannot maybe all the time articulate myself how I'm thinking or how I'm going from step A to B, how it
Mm-hmm.
occurred to me.
Hmm. Yeah.
So So I'm that is also a kind of a pastime for me to watch documentaries on particularly on computer scientists and mathematician, because it's easy for me to relate, and sometimes physicists, where they talk about how they think, literally genuinely how they think. So I'm
Mm-hmm.
very passionate about knowing how people think.
Mm-hmm.
That's
Do you think?
definitely in the spirit of the High Impact Thesis podcast. And I guess on that note, thank you very much for joining us today. We appreciate you having the time for us, and yeah, wish you all the best of luck in the rest of
Yeah,
your
thanks for
business.
inviting and thinking that my thesis is maybe high impact. That's kind of nice to hear from somebody that, oh, high impact, really? The thesis is not yet there, but you think it's high impact. So what more I can, imagine and think. Yeah. But it's a
Yeah.
process. I like it. More importantly, maybe from most of the other people, there is nothing outside research for me in my life. So that
Hmm.
helps and distracts both ways, positive and negative. So like I feel like kind of cliche, but it feels like I'm born for it. That kind
That's
of
a good attitude. Yeah, that's a good
that, yeah.
attitude.
So that
Yeah.
kind of things keep going in me. So can maybe bore some people's around because I have nothing else to talk about than other than nerdy stuff.
Mm-hmm.
So that's how
Right.
it is, and it's glad to talk to you guys, and hope somebody listens and then maybe come back to me, maybe cite
Right.
my
Yeah.
papers.
Okay. All right. Thank you,
All right.
Parikshit.
Thank you. Thank you
Thanks a
very
lot.
much.
Have a
Thanks
good
a lot.
night. Bye.
Yeah, you too, guys. Bye.